It's my great pleasure to introduce Yi Wang. Ye joined us after finishing his PhD in University Politècnica di Catalonia in Barcelona, and then worked a few stints of visiting researchers in University of Seville and Central Supelec was one of the latest one. He joined us around 6 months ago now. I don't know how far.
Yeah, about 6 months.
Yeah, so I'm looking forward to his talk. Thank you very much, Yi.
Okay, thanks, Iman. Good afternoon, everyone. Thanks for joining me today. Today, I'm going to present the work that I'm doing with Chris. And the topic is robust cooperative distributed MPC based on set membership approach. And this is the project that we started about half a year ago. We are still working on this one. And today, I'm going to share some basic ideas for this project. And also, we're welcome for the discussion on this topic. So my talk has the following 6 parts. First, I will discuss the motivation of this project and some introductions. And second, I will describe the problem formulation. And then the third part is a main result, that is the robust cooperative distributed MPC. And in the fourth part, with this robust distributed MPC controller, I will analyze some closed loop properties. And in the fifth part, I will show a very simple numerical example and some simulation result to test this controller. And finally, I will give some conclusions and some directions on the future works. So let's start from the motivation and the introduction part. And the motivation of this project is we want to develop distributed control strategies for autonomous systems. As shown in these 2 pictures, there's the mobile robot in our lab. And actually, we want to control not only one robot, because this picture I took a long period ago. And we want to control a group of vehicles for formation and trajectory tracking by using a distributed controller. And for the real application, we know there are a lot of unknown disturbance and like uncertainties from the environment, like indoor or outdoor. So these unknown uncertainties should be taken into account when we design the distributed controller. First, we want to review the cooperative distributed MPC, even in this case without the disturbance. And the task for the cooperative distributed MPC are the following several aspects. The first one, we have to deal with a coupled cost for the cooperations. And also there's a coupled constraint. For example, there's couplings in the dynamic models. And with these couplings, in order to use a distributed optimization algorithm for practical implementation, we need to formulate this distributed MPC optimization problem in a separable structure. So in this structure, we also need to define the local terminal cost and the local terminal constraint. And as we know, the closed loop stability for the MPC is mainly guaranteed by the properly defined local cost, terminal cost and the terminal constraint. And so, unlike the centralized MPC, for the distributed or decentralized systems, we can refer to this conference paper in 2009. And there is we can use the optimum function with a relaxation term at a local level. So here the term is formulated as gamma I. So which means for each agent, this gamma I, for some agent, it can be positive, and but in the global, the total gamma I should be strictly non-positive. So which means it allows the local terminal cost to increase as long as at the same time the global terminal cost decrease. So this feature can be used in the distributed MPC to define the local terminal cost and the local terminal constraint, that is a local terminal sets. And in the literature, we found these two published paper. One is from 2016. The other one is quite new from 2020 this year. And both of them use the Diopter function with the relaxation term that I just showed in the first slide. And each local terminal cost is defined as an individual quadratic term. And the matrix is a solution of the above mentioned Diopter conditions with the relaxation term. And the main difference is that for the first one, the author define a time varying local terminal set. And the parameter, this alpha, is time varying and updated in this way. And there's a term that is from the relaxation term from the Diopter condition. And with this update, there's an invariance for the state in the closed loop is guaranteed, so the stability can be guaranteed. And for the second paper, the author defined a local adaptive terminal set. In this set, also the condition of this invariance is used, and the parameter alpha I for all the agents are set to be decision variables in the distributed MPC optimization problem. So it can be obtained by solving the same optimization problem as in the MPC, and those conditions and also the Diopter stability conditions and also the constraint satisfactions are later on converted into the linear matrix inequalities and plugged in the optimization problem. And in terms of the uncertainty, when the closed loop system also contains the uncertainties, sometimes we can still use the distributed MPC, the nominal one, and because there is inherent robustness inside. But however, this inherent robustness is implicit, and there's no any guarantee for the feasibilities and also stability. So alternatively, on the other hand, we can use a robust technique to enhance the robustness for the distributed MPC. And in the literature, the two-base technique is one popular approach for the robust MPC. So the basic idea is that we can use a constraint tightening approach with the robust positively invariant sets and also local feedback gain to tighten the constraint for the state and the U and the inputs in order to guarantee the closed loop properties in terms of unknown but bounded disturbances. So in this project, we start from a fundamental problem of designing a robust cooperative distributed MPC. We also want to use a constraint tightening approach to enhance the robustness for the distributed MPC. And the main challenge we found here are the following two problems. The first one is how to tie the constraint for each agent, taking into account their couplings inside the system for the cooperative control. Besides, our goal is that we don't want to tie the constraint too much in the distributed way in order to avoid too conservative this case. And the second one, since for the nominal case, for the nominal distributed MPC, the problem is formulated in a separable structure. And also the local terminal sets are set to be varying. So in the robust case, we still want to keep this separable structure. And the another problem is that how to define the local terminal sets in the robust case. So to solve these two challenges, we first formulate the problem, and we consider discrete time linear time invariant systems with couple states and also the disturbances, and in this model, this xi is the state of the agent I, and the agent is inside the set capital M. And there's a coupling inside the state. So xni is the vector of the state, including itself is the agent I, the state of agent I, and also all its neighbor states. And the U is independent, and also disturbance is independent for each agent. And besides, we also consider for each agent, there's a state. The state and input are constrained, but by the convex sets. And here we also consider two assumptions. The first one, we assume any two neighboring agents can communicate in a bidirectional way. And the second one, for the disturbance for each agent, for all the agents, they are unknown, but can be bounded in the convex sets. And the control objective can be summarized by minimizing this state cost function. Is a very standard one. It's a sum of a weighted quadratic term for the xn, and also the weighted quadratic term for the input. And for the robust control strategy, since the disturbance are unknown, especially we don't know them along the MPC prediction horizon. So we want to use the nominal model as the prediction model for the MPC. And here we use the X bar and the U bar as the notation for the nominal model. And to solve the above mentioned two problems, we want to propose the following solutions. And for the first one, to tie the constraint for each agent, we want to use a set membership approach for that. And instead of using the RPI sets, because for the set membership approach, with bounded disturbance, we can explicitly propagate the effect of those bounded disturbance sets along a finite prediction horizon. So like the two-based approach, the worst scenario, we can remove this explicit set instead of RPI set, like step by step. So in this way, we can reach our goal. That is, we don't want to tie the constraint too much. We want to leave more degree of freedoms. And for the second one, we want to keep the separable structure. So we have to consider the fact of those disturbance in the local terminal sets. So then we define a new set, and we call it as a robust adaptive local terminal set. So from the name, it is adaptive. So the parameter for this set we also set as a decision variable, and to be optimized in the distributed MPC optimization problems. And then I will discuss the condition for finding these sets later. So next, I will present the design the robust cooperative distributed MPC. First, for the constraint tightening, we use a local state feedback controller as defined here. So the KNI is an auxiliary feedback gain for agent I. And with this local feedback gain, we can also, we would like to use a set membership approach for constraint tightening. So first, we define a state error as shown here. That is the difference between the closed loop state xi and the nominal state from the prediction model. So we can consider a finite horizon. This capital N is MPC, actually MPC prediction horizon. That is a positive integer. And we can initialize the first nominal state x bar I 0 for each agent I as the closed loop state. Actually, that is the same as in the MPC that we feedback the current state as the first predicted state. And then we can propagate this error. So for the step 0, since the initialization we set as the same value, so it is 0. And from the next step, from the step 1, we can use the model, the uncertain model with the disturbance, and also the nominal model as a prediction model to propagate this error. So for the step 1, the error, the state error is a disturbance at step 1. And similarly, from the step 2 to the end, to n-1, we can iteratively propagate this error. So at the end, we can find this error dynamics. And actually here, for the notation T, as a reminder, we use the index T to denote the prediction step, just make difference between the K in the model. That is to denote the real-time step in the simulation. So in this aerodynamics, we can see the WIT is unknown disturbance. That is, we don't know it along the horizon N. But from the assumption that we made at the beginning, each unknown disturbance can be bounded in a common set for each agent. So then we can propagate this one by this aerodynamic. So in order to find a set to bound this error. So the set we defined here as a RIT for the error. And this set can be propagated in this way. So from this definition, we can see to find the error set for the agent I at time t, it receives the previous error state of all the neighbors at t-1, and then using this Minkowski sum to sum the sets, we can find this RIT. And for all the steps in the horizon, in this final horizon N. And then for the constraint tightening, we can, from this RIT, we can also find the error set for the control input in the same way, and also based on the local feedback gain, this K. And then we can remove this RIT and QIT, that is a fact, that is explicit effects of the uncertainties for the state and for the U. So we can proceed the constraint tightening approach over this horizon N, and to find a tightened constraint for the X and U. So actually here, compared to the constraint tightening approach with the RPI sets, we can see this RIT. This set is a subset of RPI set at a local level for each agent. So the size of this RIT is smaller than the RPI set for each agent. So this constraint tightening approach is less conservative than the one using the RPI set. So the next task is to define the separable terminal cost. So here we also use this quadratic form for finding this local terminal cost. And there's a matrix that is positive definite matrix PFI, and also there's a corresponding terminal feedback control gain KFI. We can find it from the solution of the optimal condition with the relaxation that we present in the introduction part. And it was mentioned that this KFI could be different than the local feedback gain KNI that we used for the constraint tightening approach. Because the objective for finding these two gains are different, I will talk about later in the closed loop analysis. And the next one is the robust adaptive local terminal sets. So in general, we give the definition as shown here. It is defined in a ellipsoidal form. So the parameters are the matrix Fi and alpha I. And these two parameters control the size of this ellipsoid. And for the practical reason that we can fix Fi to be PFI, that is a matrix used in the local terminal costs. And then we set the alpha I as the decision variables in the optimization. And to find this set, we give the condition for that. And this condition states for any state of the neighbor for the agent I is in a local terminal sets, and to propagate for the next step together with the error, that is a tighten error defined in this way, start from a set wi, and then tighten in n-1 steps. And the next this combination should be inside the terminals, the local terminal sets for the agent I, and this set later on will be transformed into the IMI condition and then plug into the optimization problems in order to find the alpha I. So then in general, we present the optimization problem formulation here. So this problem is in a separable structure, including the stage cost function, the local terminal cost, and the local terminal constraint for each agent I. So this optimization problem can be implemented in a distributed way by using a distributed optimization algorithm, for example, ADMM. And then the optimal control action at time k can be assigned by using the receding horizon strategy. That is the first value of the optimal solution of input u. And here, because we feedback the current state xik as the first predicted state, and also together with the constraint tightening approach. So for this one, unlike the standard robust MPC, there's no feedback gain used for implementing these optimal control actions. So it's just the first value of the optimal solution for the U. And then with this robust distributed MPC, we also want to analyze the closed loop properties. Before that, we first made some assumptions. The first one, we need to give the positive definite weighting matrices that is used in the stage cost functions. And the second one, for finding this local feedback control gain K and I, we want this gain can stabilize the global system, and also the sets, because this gain will be used for the constraint tightening. So we want the tighten constraint at the end of the horizon are not empty. So all the constraints are not empty. And for the PFI and the KFI, they can be found from they should satisfy the Lyapunov condition with the relaxations. And here we can see the difference for the KNI and the KFI. So the objectives are the different. So they don't have to be the same local feedback gains. And also the last one is the local terminal sets. So it should satisfy the condition that we gave before. And also this set for sure will be inside we should guarantee that this set should be inside the constraint for the state and input. And with these assumptions, first, for the first properties, we can have the recursive feasibility. So which means starting from any feasible initial condition, the closed loop system is recursively feasible for any unknown disturbance within the common sets. So which means if the closed loop system is feasible at any time k, and then it is also feasible at time k+1. And for the proof, I'm not going to show all the steps. I just present the basic ideas. so here the proof is similar to the robust MPC. So because we can consider the optimization problem is feasible at any time k, so then we can use all the optimal solution at time k to define a shifted input for the next time step, that is k+1, along the finite horizon n. So here we can define a shift input for the k+1, and from the step 0 to n-2, and with this gain kni. And for the last step, that is step n-1, we can define another shifted step with another term. This is a terminal feedback gain kfi. And then with these two shifted control inputs, we can check all the constraints in the optimization problem are satisfied at time k+1, and then we can complete this proof. And for another property, that is, we can prove with this robust cooperative distributed MPC controller, the closed loop system is input to state stable. So for any feasible initial condition, the closed loop system is always input to state stable for any disturbance inside the convex sets. And for the proof, the idea is to prove the closed loop MPC cost is an ISS Lyapunov function. So then use the result from this paper from mainly from Professor Daniel Limon. Since we can prove the cost is an ISS Lyapunov function, and then the closed loop system is ISS stable. Then we just run a simple numerical example to test this proposed robust distributed MPC. The numerical model that we use is a mass spring damper system in 2D. This is just very simple example. We just want to first run to test this strategy. So this is with two masses, and there's two springs and one damper connect two masses, and there are 4 states. Just denote the position and the velocity, and for the input is two forces for these two masses respectively, and we also consider additive disturbance for each mass that can be bounded in these convex sets. And as the dimension of this system growing, if we plug in more masses, we may see the advantage of this robust constraint tightening approach, because we tie the constraint in a distributed way. So as the dimension of this system growing, we can those explicit sets that we use for the constraint tightening are with not too high dimension. So then we can easily implement a constraint tightening approach using the set operations. So in the simulation, we also transform the conditions for the robust adaptive local terminal sets into the LMI conditions, and we also plug in the constraint. This set should be inside the constraint for the state input, and then also convert it to the LMI conditions. And then we run this optimization problem online in real time, and with some sampled disturbances with random values within the given convex sets. And from the result, this is just a simple run. From the result, we can see the closed loop state trajectory. This is the first figure is the state. The second one is the input. They are both stable and converging to the coordinate region. And besides from the optimization solution, we can also abstract the solution for the alpha I. And in this case, since this system is 2D, so we have two alpha, that's alpha 1 and alpha 2. So in this case, from the online solution, the terminal site, the size is decreasing and until reaching a neighborhood of constant values. So finally, I will talk about the conclusion and some future works. As a conclusion, in this project, we have formulated a robust cooperative distributed MPC, and we studied a robust constraint tightening approach based on the set membership approach. And we define a robust adaptive local terminal set, and also we gave the condition for the design. And we have also proved the closed loop system to be recursively feasible and SS stable. And we have sent this preliminary result to the CDC this year, and hopefully we can discuss more there. And as a current and future works, now we are working on the distributed synthesis for all the parameters used in this optimization, this distributed MPC formulation, such as there are two types of feedback control gain. One is for the constraint tightening, the other one is for the terminal setting. And also we want to find all the IMI conditions for the robust adaptive local terminal sets. And finally, we want to apply these robust control strategies for the autonomous groundware equals. And in the future, we also want to find a suitable distributed optimization algorithms and for implementing this optimization problem. And also probably we can try to improve the performance, like convergent speed and so on. And that's all for my talk today. And thank you very much. So if anyone has questions, I'm very happy to discuss.
So thanks. Anyone has any questions? I just wanted myself a clarification on, okay, Emily, and you ask after me. On your slide 17, you said something is less, your proposed method is less conservative than, I didn't quite follow why you could draw that conclusion.
You mean 17?
I think on slide 17, yes.
Okay, yeah, just.
You're going to way back.
No. I didn't type too much, but I don't know why it go very fast.
Yeah.
Here. Yeah, you mean here?
Yes, I couldn't follow. Yeah, can you please clarify what's going on here?
Yeah. So yeah, I should put more formulation here. So what I mean is less conservative in the sense that we remove some part for the constraint for the X. This set is smaller than the RPI set because we remove step by step. So at the beginning, we don't remove anything because we feedback the current state.
Yeah,
so
okay.
So the constraint is the original one.
Yeah, but at the end of the horizon, it is the RPI set, right?
No. I never use RPI set.
Okay. Okay, I have to think about it a bit.
This is a propagation. This is like a cut, like a piece of RPI set.
Yeah. Okay.
So then it's I can say it's less conservative.
Mm-hmm. Cool. Thanks.
Yeah.
Emilian, do you want to ask your questions?
Yes. Hi. Thank you. I had a question about your slide 15.
Yeah.
I think so. Yes. So here you consider that you have an initial error in your MPC that is 0. I think so.
Yes. Yeah.
Could you consider that it is non-zero, that you don't really know your initial condition and make it robust anyway?
You mean the center of the set is non-zero?
Yes, yes.
I think it is possible.
Yeah, because it could, I mean, be used to in the case where you don't have your precisely your initial state, because
Yeah.
you have measured it in some way and it's not precise enough.
Yeah.
Okay.
Yeah.
Nice.
Yeah.
Thanks.
Can you see Andre's question in the chat?
Not in the chat. No, there's no.
Okay. Andre, can you ask the question? Because I think you just sent it to me. Yes, you just sent it to me.
Can you hear me?
Yes, yes.
Yeah, I sent to you, Iman. It was private message.
Oh, okay.
Yeah, so how do we guarantee that the errors stay inside the error bounds if we don't apply the feedback law we used to design these error bounds? I didn't quite get it.
Yes. So there's actually is quite a strong assumption that is we need to bound the disturbance only. So all the guarantee is based on this. So we have to say at the beginning that all the unknown disturbance are bounded in a given set.
Yeah, I see, but that was not the question.
Yeah. Okay.
I mean, we have designed the error bounds.
Mm-hmm.
I believe they were called R, like big R.
Yeah. Yeah, here.
Assuming that we have the feedback laws given by an engineer. And then what you're saying, we don't have to apply these control laws, and we can just apply the open loop control solution obtained by solving the optimization problem. Is that correct?
Yes. Yes. So actually is for the optimization problem. Yeah, you are right. This K, we don't use it because we have considered to find the optimal solution, like a suboptimal solution, based on this K, and this K is plugged in the constraint, right? So this error in the closed loop can be attenuated by this K from the solution that we pick up from the other constraint. Do you understand me?
Probably, yeah. Seems like I have to think about it more.
Yeah, because we use that K just to attenuate the error in the closed loop.
Don't you use this case to design constraints tightened sets?
Yes,
No?
yes, exactly. Yeah.
And then in the tube formulation, in the tube approach, you have to still consider the same feedback laws to guarantee that the errors stay within the error bounds. Is that correct?
Yes.
To verify that your assumption holds, like to verify that your tubes stay of the same size as you expect it to be, you have to apply the feedback laws you used for designing these tubes.
Yes.
And now you're saying you don't have to use these feedback gains.
What I mean I don't use is only for implementing the optimal control action at time K.
Okay, I'll try to think it more. Yeah, I don't quite understand that. Yeah,
okay.
So, thank you for answering.
Yeah.
Okay, is there any other question? Okay, if there is no other question, let's thank Yi again for his talk and looking forward to meeting all of you next week. Thanks, Yi.
Okay, thanks.